In this tutorial, we will learn how to run a simple linear regression model in R. And specifically in this tutorial, I will show you how to use the regression function from the lessR package to run a simple linear regression model. So you should have RStudio open. Let's now go to File, New File, RScript to open up an RScript file editor or RScript editor. And I'm going to make a quick note here using the hashtag annotation that this is simple linear regression in R. Okay, so the data file that we're going to be working with is in my working directory folder already, and it's called selectionexercise.csv with a capital S and a capital E for exercise. And so before reading it in, I'm going to note that I'm going to read in the data. And I will use the install.packages function if I haven't yet installed the reader function, which is what I'm going to, or the reader package, which is a package that has a function that I'll use to read in the data. I have recently installed the reader package here, so I am not going to run this line of script here. I will, however, run the library function or with the reader package name in the parentheses. So you may, if you've never used the reader package before or you haven't updated it recently, I would recommend go ahead and run this line of script here by clicking run. But definitely at the very least, you will need to run this, the library function with the reader package name here. Click run. Okay, we see down in the console that worked. Now, the next thing I'm going to do, and I'm doing this a bit out of order, but it doesn't really matter in this case, is I'm going to set my working directory. So I'll set working directory, and I'm going to do so by using the setwd function from base R, and I know my working directory off the top of my head, which is my H drive R workshop folder here. And make sure it's all in quotation marks. Alternatively, you could go to sessions, set working directory, choose directory, and then you'd open up and select the folder that contains the data file that we're going to be working with today. So I'm going to go ahead and run this line right here to set my working directory, and you can see down here in the console that that worked. Okay, the next thing I'm going to do is continue the read-in process for the data. And so I'm going to use the read_CSV function from that reader package, and I'm going to name this data frame that I'm going to read in, or the data I'm going to read in, as a data frame object. And I'm going to call this data frame object selection because we're going to be working with employee selection data here. And I'll use the left-handed arrow operator here to note that I'm going to name and create that new data frame object. And again, I'm using the read_CSV function from that reader package. And the exact name of that file that I'm going to read in from my working directory folder is selectionexercise.csv. Okay? And if I go to my working directory folder, I can verify that. And here we go, selection exercise right here. And you can see it's a comma separated values file, so it is .csv. Okay, so let's read that in. Okay, it looks like that was successful. So let's click on the name of this new object, the data frame object called selection, in our global environment and take a look and see what we have here. Well, we have an ID variable. This is our unique identifier variable for these employees. And let's assume this is a concurrent validation selection system or a current validation study that we're doing on a selection system. And specifically, we're looking at 3 selection tools and the extent to which they are going to predict job performance. And by concurrent validation, I mean that we're using current job incumbents here. Let's assume these are people 90 days after hire. They've been on the job for a while. We're going to give them these selection tools. It's not consequential for their future in the organization, but we can use their data and their recent 90-day probationary, let's say, performance evaluation score, and see the extent to which a situational judgment test, an emotional intelligence test, and a proactivity test predict performance. So a concurrent validation design is one way that we can, that'll make a note here, concurrent validation design. And it's another way of assessing, or one way of assessing criterion-related validity of selection tools, okay? So in this exercise, we're just going to focus on the SJT, which is the situational judgment test selection tool, and our criterion of interest, our outcome of interest, is this performance variable here. Okay, and so let's assume for both that higher scores mean higher levels of performance and scores on the situational judgment test, which we assume is a good thing here. Okay? All right, so how many rows do we have? Well, and this will tell us how many people or job incumbents we have in this concurrent validation design. And so we can use the in-row function from baseR. And we can type in the name of our data frame, which we called selection with a capital S. Click run. So we have 300 people here. So that's our sample size. And then we can also use names if we would like. The names function from baseR to ask, okay, what are the variable names or column names for this data frame? And so we just put the name of the data frame in the parentheses there, and we see what we just saw a second ago. Okay, so it's important to note that when we're running a simple linear regression, that there are statistical assumptions. Okay, so with any type of inferential statistical analysis, there's going to be some statistical assumptions that we need to meet, or at least have evidence that we have come close to meeting them. Okay, we're never going to perfectly meet these assumptions in most cases. Instead, we need to justify our use of a particular analysis by saying, hey, you know what, this looks like reasonably we're coming close to meeting these statistical assumptions based on different type of diagnostic tools that we can use. So let's start with some of those diagnostic tools. And so what we're going to do first is let's look at the assumptions of bivariate normal distribution. I'll show you what that looks like in a second, that the association is linear, and that we have no bivariate outliers. Okay. All right, so these are the first three assumptions that we're going to eyeball, so to speak. And we're going to use the package called lessR because it has a function we'd like to use, the scatterplot function. And so we can use install.packages, and in the quotation marks, we'll put lessR. And I'm not going to run this, but make sure you do update this package frequently. I just did a moment ago, so I'll save us the time and not go through that. But if you haven't updated it recently, click run to run that line. And after you've done that, or if you have already installed this recently, just type in the library function in lessR without quotation marks as the sole argument in that library function, and then click run. Okay, so we can see down here that that worked. Okay, so as I mentioned, there's a scatterplot function from lessR that we're going to use. And so it's scatterplot with a capital S and a capital P. Now, alternatively, you could use the plot function from baseR to do this as well. We're going to use scatterplot function here because it does have some additional features that are quite nice when it comes to visualizing our data and testing these statistical assumptions. And so the first thing we need to do is enter our X variable, or predictor variable in this case. Let's call that SJT, which is, again, we saw here that's the name of the situational judgment test variable. Then we enter the second variable, which is our criterion variable, which is performance in this case. And then as our third argument, we need to use data equals and the name of the data frame from which these two variables come from, which is data equals selection here. And then let's add on one other thing, which is there's an additional argument we can use, which is ellipse equals true. And if you want more information on the scatterplot function, check out the corresponding tutorial called Scatterplots in R, and you can find out more there. But the ellipse equals true will provide an ellipse around our scatterplot, which will give us an idea of the extent to which we have this bivariate normal distribution I just mentioned. Okay, so let's go ahead and run this script there. Okay, so here's our scatterplot. SGT on the x-axis, performance on the y-axis here, and here's that ellipse I was talking about. And so you can kind of see that, one, we're meeting that assumption of a linear association here, because you can see that there doesn't appear to be any notable non-linear dynamic here. It seems to be mostly a linear positive relationship that we can see here. Okay, again, it's not going to be perfect, but we can see there's some evidence for that here. We also see, here's that bivariate normal distribution. We're looking for that football shape or American football shape here. So this oval here. This is what would really signal to us that we have a bivariate normal distribution between these two variables. Bivariate means two variables, normal distribution. So bivariate two variable normal distribution is what we mean there. And the other thing that we're trying to determine is whether or not this is free of bivariate outliers. And you can actually see that there might be some potential candidates here. And if you actually go to the output here, you can see the extent to which we have the extent to which these are associated in terms of a correlation. So here's actually the correlation. So this is an effect size here, standardized metric that describes the strength of the association between these two variables. 0.417, we can see the p-value here is less than the conventional alpha of 0.05, two-tailed. And so we could say that this is a statistically significant association. Now, actually, that is one place that you could stop. You could say, this is my criterion-related validity coefficient, is my correlation coefficient here, and that's perfectly fine. However, if you want to use the data here in this sample to find out what this association is and create that line of best fit, well, then you can go with additional sample data and then predict using news scores on SJT what their likely performance is going to be, okay? All right, so we've found some evidence that these first three assumptions seem to be met, but let's keep on going here. And what's really cool about the regression function from the lessR package is that it generates a number of plots automatically that help us test these statistical assumptions, and it provides other diagnostics as well in table form. Okay, so it's really simple to use the regression function from lessR. Again, to use it, you need to make sure that you've accessed the lessR package using the library function. And you just simply type regression with a capital R. And then you're going to specify your regression model. And the way that you do this in R, or at least that you typically do this in R, is that first you list your outcome variable. So that's performance. And then the tilde symbol. And then your predictor variable here. So this is actually our regression model. So our outcome variable, or criterion variable in this case, comes to the left of the tilde. Our predictor variable comes to the right of the tilde. And so what this is saying is performance is regressed on SJT. And that's another way of explaining what a regression model is here. And then we do data equals and the name of the data frame from which both of these variables come from. Okay? And so this is actually it. This is all we need to enter to run a regression model. This is actually a really nice function. It packs a lot in. So let's see what we get using this regression function and specifying that simple linear regression model. Okay, so before we get to the output in the console, let's take a look at the plots we have available here. So I'm going to scroll back. There's 3 plots. This is the first one. So another statistical assumption that we need to meet in order to run a simple linear regression model is that the residuals are normally distributed, okay? And so you see this right here is a histogram of the residuals. And if you don't recall what residuals are, they're the error values. So it's our error in prediction, okay? So we want those, if we just take all those errors across all the prediction points, so it's the extent to which, if you think about our scatter plot back here, if we were to imagine that line of best fit, the extent to which these different points, which are cases, deviate from that line, okay? So that's our residual there, the error. So here we can see a histogram representing that, and then we have superimposed here a perfect normal distribution, and then we can actually see the density here of our histogram, and you can see that this is actually pretty close here to a perfectly normal distribution. So I would say we have pretty good evidence that we've met that assumption, okay? So met assumption of normally distributed residuals or errors, okay? And I'll say based on the residual distribution of residuals plot, okay? So we've met another assumption, or at least we have some evidence to support that. Now, the next thing we'll do is we'll use the arrow here. And I should also point out, you can export these by each one of them by copying to a clipboard or saving them as an image, okay? And if you want to zoom into them, you can do this as well. Okay, so this next plot is our fitted values, which you can think of as our predicted values. Technically, predicted would be reserved for when you're truly doing predictive analytics, but that's what we're talking about here. So these are the values of, if we use the regression model that I'm going to explain to you in a second to predict the outcome variable, okay, these are the values here that we would actually fit, okay? So the values, so these are the line values, in other words, okay, that would fit along our regression line of best fit. Okay, and then here on our y-axis, we have the residuals. All right, so one of the first things that this is helpful for testing is the assumption that our average residual error is 0 for each level of the predictor. So you can infer from these fitted values that if we look across here, here is 0. Okay, so here would be 0 is this dotted line here. Ideally, we want a perfectly straight solid line overlapping completely this dotted line here, because that would indicate that our average residual error is about 0 for each level of the predictor variable. Okay. Now, here you can see you get a little bit of a deviation there. This is actually really good, or pretty good from our standpoint. We'd be pretty excited about this. This is pretty good justification that we've met that assumption. So we've met assumption that residual, let's say, error is 0 for each level of predictor. Okay, and again, we're inferring that predictor because we have the fitted values is going to be based on the levels of the predictor here. Okay, so we're using those predicted values to predict these values here. Okay, so that is one assumption. Another assumption that we can help meet using this particular function, or this particular plot here. And let's just add that this plot is the residuals versus fitted values plot here. Okay. Now, another assumption that we can help meet using this plot is that the variances of the residuals are equal, okay, across different levels here of the predictor variable. And so what that means is that we don't want to see, for instance, like a funnel. So if we saw that the variance or the spread in these points here was much larger here and then much narrower here down at the end, or vice versa, that would indicate that we probably violated that assumption. This is actually pretty good. The variances of the residuals look pretty good. They look pretty even across. And so this is what we would call the assumption of equal variances, or homoskedasticity of variances. Okay. If we had unequal variance, we'd call that heteroskedasticity. Okay, so I'll type that out for you. So we seem to have met assumption of homoskedasticity of variances. Okay, and it would be just replace this with homoskedasticity of variances if you fail to meet that assumption. So we're saying that we have equal variances across levels of the predictor variable there. So that's good. And so this is based on this residuals versus fitted plots values plot again. Okay. All right. So here we've been kind of ticking some things off here, but one other thing that we start to note here is that, well, maybe we have some outliers here. So this actually flags row number 233, the case corresponding that might be a potential bivariate outlier here. Okay. So now let's, I'll actually tick forward there. We're not here yet. This is something that we can use to interpret the overall model in a second. But what we will do now is let's go to our residuals and influence component of, this is a table that's in your output for the regression function towards the bottom. And you'll see here that we have the SJT scores, the predictor variable scores, the outcome variable scores, and the fitted value. Okay, so here we can see for case 233, their SJT score that they actually have, their observed value is 10, and their observed performance is 25. However, based on the regression model, which we'll look at in a second, it predicted this is 13.757 as their outcome variable there. Okay, and so here you can see the residual, which is just simply 25 minus 13.757 is your residual here. Okay. Now we also get some estimates here of outliers, and in particular, we're going to focus on the bivariate or multivariate outlier indicator of Cook's distance, or Cook's D. And generally higher values mean that more likely that this candidate is going to be, this particular case is going to be a bivariate outlier. Now we're typically looking for cases too that seem to deviate from the rest. And here we can see cases 201, 70, 170, 70, they tend to be they're pretty closely clustered together. But this one is 0.121 as opposed to 0.076. And so the row number associated, or the case associated with row number 233 seems to be a candidate that might be a bivariate or multivariate outlier here. Okay. Now, with that said, there's really no hard and set rules. There's rules of thumb that people have for in terms of what's the high Cook's distance value and so forth. And this is one that you really need to look across all the values and look for patterns and ones that really stick out here. Generally, once you get about above 0.05, you should start looking a little bit closely at these. And especially when you see this one, this might be candidate for potentially removing from the data. Okay. Now, I am always hesitant to drop anything, drop a particular case that might be an outlier, and we should always have really strong justification for this, okay? And the reason is that this might be a very realistic value here, that this combination of SJT and performance here might be very, very realistic in our underlying population, and maybe we just didn't sample well to begin with. And that's actually another thing. There's a statistical assumption that's harder to justify with any of this here, the information we get from these plots and so forth and from these diagnostics, and that is the assumption that the cases are randomly sampled from the underlying population here, okay? And if we did have a perfect random sample, then we could assume that this sample is representative of the population, okay? But because that's really hard to know, we now have to be kind of cautious if we're going to remove any outliers, because it could be that there's a lot of people like this. We just happen to only capture one of them, and so it appears to be this bivariate outlier here, okay? But that's how you interpret this and this output. Okay, so let's say at this point, let's table that for now. Let's talk about potentially removing case 233, row number 233, the person that's associated with that case or that particular row number. Let's consider removing them later. But for now, let's just run the model or interpret the model as is. So, okay, so now we can start looking through some of the other diagnostics or looking through the actual model that we have here, okay? And so let's start with the top of the output here. So first you have your background section. It tells you what your data frame name is. It tells you what your response variable is, which is another name for your criterion variable, your outcome variable, your dependent variable, whatever you want to call it. We also have our predictor variable here, which is SJT. And then we have the N, so this is your sample size. This is the number of rows or cases in the data, as well as how many were retained for analysis. So by default, there's list-wise deletion, which means that if any one of these cases, for instance, for SJT and performance, if there was missing data on one of these, it would drop that case for that person, okay? And then drop them out of the analysis. Okay, so the next section, and this is really of substantive interest, is our basic analysis section here. This is where we get our estimated regression model. Okay, so how do we interpret this? Well, you'll see because we have a simple linear regression model, we have two rows here of interest and then multiple columns of different information that we're going to interpret. So the first row here is the intercept. Okay, so if we look at this plot here, the point at which conceptually, so if you imagine 0 here, that when x is equal to 0 or the predictor variable is equal to 0, and you can imagine the y-intercept crossing or the y-axis crossing there, where this line of best fit here crosses that intercept or the y-axis, that's our intercept value there, okay? So in this case, it's 6.939, okay? And you do see that we get our standard error, the associated t-value and p-value, which is the test of statistical significance. What this would be testing here, if this is statistically significant, the p-value is less than 0.05, two-tailed, which is a conventional alpha level. If it is less than 0.05, then we would say that this intercept value is statistically significantly different from 0. Okay, that's not usually of substantive interest, but we do retain this particular value for the future when it comes to predicting or when it comes to creating that line of best fit, because you need to know the x or the y intercept and you need to know the slope. Okay, and here are the confidence intervals, 95% confidence intervals for that. What we are typically interested in substantively when we are trying to assess the criterion-related validity as part of this concurrent validation design here that the data come from is the extent to which our predictor variable, our selection tool in this case, significantly is associated with our outcome variable. And here, this is what this row shows. Here is our unstandardized regression coefficient or slope or weight, however you want to call it, which is 0.682, the standard error, the t-value, and the p-value, which is what we're ultimately interested in here along with the estimate. And what this says is that because this p-value is less than 0.05 two-tailed, we would conclude that there is that this value of 0.682, this regression coefficient, is statistically significantly different from 0, meaning that we can treat this upward slope that we see here, this regression coefficient, this slope, as being statistically significantly different from 0. Okay, so there's a positive slope here because this value is positive. Okay, and we see that evidence here in this plot. And we get the 95% confidence interval from which the population value likely falls within this interval here. Okay, and this gives another idea. Now, keep in mind this is an unstandardized estimate, which means it keeps it in the raw metric of our SJT variable and our outcome variable, which is performance here. And so what does this mean? Well, you could interpret this as being for every 1 unit increase in SJT, performance increases by 0.682. Okay? So that's a way you could interpret this is interpreting it in terms of that type of language. Okay? Now, the next thing that we're going to do is I'm going to show you what this actually looks like in terms if you want to envision this as a line. So let's envision, and keep in mind this is actually y predicted here. So this is our outcome predicted. In fact, let's just call our outcome what it is, which is performance. And I'll just do a little dash and say predict, so that's our predicted value. Okay. Well, what's our intercept value? It's 6.939. So let's copy that, paste. Okay, so that's our intercept right there. That's our constant that we're adding to the line. And then let's paste in our regression coefficient. Okay. And let's say multiply that by our whatever observed variable we have for the SJT. Okay. So this right here is a line. Okay. This is the equation for a line here. Here's our slope. Okay. And then we can plug in different values using basic algebra. So let's take a look at that actually. So watch what happens if we, instead of just putting a placeholder for whatever SJT variable we observe, let's say we get a situational judgment test score for a new applicant of, what do we want to say? Let's say it's 6. Okay, so they score a 6 on this assessment here. Okay, well, we can actually run this and we see here's the predicted score right here. It is 11.031. So if we paste that there, okay, so this is what we would predict if someone got a score of 6 on the SJT in a future sample, or let's say future applicants. We would expect them to have a performance of 11.03. Okay, so this is how you can use that. This is how we're actually using prediction here to predict people's scores into the future. Now, in this case, we're not actually doing a cross-validation or a test model to verify our prediction accuracy, but this is the first step in predictive analytics here. Okay. All right, so now let's scroll just below the basic analysis section in the estimated model. We have the model fit section. Okay. And you can see here that we have 2 metrics we want to look at, and that is the R-squared value. You can think of this as the unadjusted R-squared value. So this is going to be sample specific here. And then we have the adjusted squared value, which is adjusted for the number of parameters and sample size that we have here, the number of predictor variables and so forth that we have in the model. And we usually, the adjusted R-squared is going to be visibly less than the unadjusted R-squared. Sometimes though, because these have been rounded, it won't be evident to you. And so generally speaking, you want to report both of these, and at the very least report the adjusted R-squared because it's actually referencing the population of interest. It's a more accurate indicator of model fit for the population. Because remember, we have some sampling error here. We just have a sample of people from this theoretical population. And so what does the R-squared value mean here? Well, this means 17.4 or 17.1 means that approximately that SJT, the predictor variable, explains approximately 17% of the variability or variance in performance, which was our outcome variable. Okay? The higher this is, and it can range from 0, the R-squared from 0 to 1, the higher it is, the better your model fit is. Okay? And below this, you get the F statistic and the degrees of freedom and the p-value that is corresponding with these r-squared metrics here. And so the p-value, because it's less than 0.05, this would signify that this r-squared value is significantly different or significantly greater than 0. Okay, so this is significant r-squared value. Now this p-value, because we have a simple linear regression model, it's actually exactly the same as this, okay, because of our regression coefficient here, okay? But what this is essentially saying is that this model with this single predictor variable SJT outperforms a model with no predictor variable in it, a null model, in other words, okay? Sometimes called like an empty model. Okay, and so we also have the ANOVA analysis of variance section here, and we can go ahead and ignore this, but you'll actually note that this is the exact same F value that we saw above here, and this is the same P value that we see here as well. But you get your sum of squares, mean of squares, and so forth, okay? Now, moving on down, we also get the correlation matrix. Remember, we also saw the correlation earlier when we ran that bivariate scatter plot, but here's the correlation again, it's 0.42. Okay, why is it pumping this out? Well, this is actually really helpful because this isn't, our regression coefficient here is unstandardized, okay? You can't compare this to other regression coefficients in this model if you had more than one predictor or in other models. The correlation coefficient is an indicator of effect size, and so if you use the standard rules of thumb of 0.3 being medium, 0.5 being large, 0.1 being a small correlation, and that's the absolute value, so positive or negative, that this is between medium and large, so we could call this a medium and large effect size, okay? Now, we could have also used, you can actually derive, if you were to take 0.42, okay, and I'll actually do that here. So if you take 0.42 and you square it, okay, this creates an r squared. You get 0.7176. Now, due to rounding error, this is not exactly the same, but if we didn't have the rounding error, you would get here, 0.174, okay? So r squared is literally r squared when we have a single predictor in the model, okay? It's just the correlation of the variable here squared. And so by that logic, we also can take the square root of those standards. So I was just talking about with correlation. Okay, so with correlation benchmarks, let's call these, you have 0.1 small, 0.3 medium, and 0.5 large. Well, with r squared, it's actually going to be, we can derive these benchmarks simply as this, which is that it is 0.01 is small, 0.09 is medium, and 0.25 is large. And so how did we come up with those? Well, we just took the square root of, let's say, 0.5, which is for the correlation, take the square root of that, and you get, I'm sorry, 0.25, or 0.5 square root here. 0.25. 0.25 square root and of the r squared here, because it is squared, you take the square root of it and you get 0.5 here. And so that's how we get back there. Okay, so we could interpret either one of these in terms of interpreting the practical significance or effect size. We'd call this medium to large here, r squared value, or we could interpret the correlation coefficient directly there. Okay. Now, the forecasting error section down here is this idea of actual prediction. So you'll get your prediction intervals here. We're not actually doing true prediction here because we only have a single sample and we haven't done a training data set and a test data set or our original data set and our cross-validation data set. That's for another tutorial, okay? So we can ignore these for now here. But this is essentially how you run a simple linear regression. There's other ways you could do it using the lm function from base R and run these all the diagnostics separately and so forth. And more than likely, you'll eventually use that lm function from base R because it's useful for integrating with other R functions that you might use down the road. And for now, though, this is your tutorial on simple linear regression in R. So in this tutorial, we tested some of the statistical assumptions, reasonably felt that we met some of them, and ran a single model. Now, as I mentioned, we're also going to, I'll show you how to remove a potential outlier. And before we do that, I also want to note that you can also get the standardized regression coefficients pretty simply here. And so how do we do that? Well, the standardized regression coefficients, and I should note you would want to put hashtags in front of these so this doesn't actually run here. And so you'd want to replace this down there in case you're following along exactly there. But let's go back to and copy our regression model syntax there. And let's paste it here. And how do we get standardized regression coefficients? Well, we just add this argument standardize equals and true, okay? And I'm actually gonna switch this to, there's a function, because the standardized regression coefficients will have the exact same associated p-values, significance tests, and so forth. And so for that reason, we don't need all the diagnostics because it's essentially the same model here. So we can use, there's a short form in the lessR package of that regression function. It's just reg.brief. And it just gives us brief output less than we normally get. And so here you can see if we go down to our estimated model here, this is rounding error. The intercept should be 0. But what we're interested in here, because in a standardized model, we don't have an intercept value, or it's 0 in other words. Here is the standardized regression coefficient. And notice it's 0.417. When you have a simple linear regression model, so only a single predictor variable in the model as we have here, the regression coefficient standardized is going to be equal to the correlation coefficient, okay? And you have the exact same significance tests as I mentioned. R squared values are the same and so forth, okay? Now, what happens if we want to remove an outlier case? So let's go back to our initial model. Let's not use let's just do these default unstandardized regression coefficients. Well, what if we wanted to remove that outlier? Well, there's an argument called rows equals, and in parentheses, let's put our ID number, okay, or ID variable, because remember we had that case, it was row number 233. We scroll down here, row number 233 is right here, and just so happens with this data frame here that the ID, unique identifier variable, is also 233. So because of that, we can say, let's just exclude this case here from analysis. And so all we do is we can do ID is not equal to, using the not equal to operator, and 233. And this will just remove that row associated with that unique identifier variable. So let's go ahead and run this really quickly. And what you'll find here is, here's our output once more. We've just removed that row, and you'll see that now we're down to 299 cases as opposed to 300. And you'll see the regression coefficient, which originally was 6.939, unstandardized, is now down to 0.644. And because we removed that person, actually we see that the model fit has gone down a little bit here. Okay, so it's actually a lower R squared value. Okay, it's still statistically significant, but, and we can see the correlation between the two values is actually slightly lower too, which also makes, between the two variables also makes sense. And so what this tells us is that, okay, that outlier seems to be somewhat consequential, but it's not really having that big of an effect when we take it out, okay? So again, I would err on the side of leaving them in unless you have a really compelling reason for dropping out those bivariate or multivariate outliers, okay? And so what we found here is evidence for criterion-related validity for this SJT selection tool in relation to performance, and specifically within a concurrent validation design. Now, this is a medium and a large effect that we found here, and we can use the model that the equation that we derived here, or in the one where we removed row number 233, we can use this to predict future values by just plugging in scores on our predictor variable into the model here. And this is essentially what we're going to do when it comes to cross-validating a model at some point in the future. All right, so this wraps up the tutorial on simple linear regression